Hi, I hope I'm audible, right? Okay, so I'll wait till I think 6:10 to start, all right? So that if there are others to join, they can join. All right. Since it's 6:10, I won't wait to start anymore. If others will join, they'll join later. I'll let them know. All right. So since it's you, just you today, did you attend the Friday session?
Yes, please.
Yeah. So most of these questions will be a repeat of that, but I'll still go through it since I can put it online. All right. A few of these
Sure.
questions are not something that you might be tested on, but it is related to the subject, so I thought it might be interesting for you to solve it. Okay. So, welcome back to the Bioreactor Design Analysis problem solving session, and it's week two. So, this week you would have learned all about the batch reaction, right? So, the questions I'll be taking today will be pertaining to the batch reaction itself. Okay. So, let's move on to the first question. So the question number one is assertion reason type of question. So what you have to ensure when you're solving questions like this is to see if the assertion and the reason are separately correct or not, and if together they make sense or not. All right. Um, the assertion could be correct, the reason could be correct individually, but you know it might not pertain to each other. So let's see what the case is this in this question. So the assertion that we're making is engineered Arabidopsis thaliana cells, and these are a kind of plant cells, a model plant cell, right? Are cultured to high density for production of polysaccharide gum. Oxygen limitation may occur in the system if there is an increase in cell concentration over time. Okay. So the reason that they have given is in a system, oxygen limitation usually occurs when the rate of oxygen supply exceeds the rate of oxygen consumption. What do you think the answer is? Is the reason and the assertion correct? You would have seen this in the last uh, session. So you will already know the answer to this. Forgetful? That's not a problem. So yes, it's okay. What do you think it is? Do you think the assertion is correct or not? Do you think oxygen limitation may occur? C. A is true but R is false. Do you? What is the reason that you're saying this? Why do you think R is false?
Because in B, when the rate of oxygen supply exceeds the rate of oxygen consumption,
Hmm.
it means you've got more oxygen
Yeah.
in the system.
Yeah.
So
That is not an oxygen limitation, right? That's an
that's not a
oxygen
limitation.
excess.
Yeah, yeah.
Yes. So that is correct. So engineered Arabidopsis thaliana cells are cultured to high density for production of polysaccharide gum. So oxygen limitation may occur in the system if there is an increase in cell concentration of time and you're not giving enough oxygen. And the reason is the opposite, right? So it might happen when the oxygen supply is not enough to keep up with the amount of oxygen that is being consumed by these cells. Okay. So C is correct. Okay.
One question.
Yeah.
When you're making an assertion, let's say A.
Yeah.
So does it always have to be true?
No, it doesn't have to be true. In that case, both A and B will be false. Since you're making a false assertion itself,
Okay,
the
okay,
reason can also be, even if the reason is true in case the assertion was right, but you made it so that the assertion itself is wrong, right? So even
okay,
if the reason was correct, the entire thing would be false, right?
okay, fine.
Because you don't know what assertion for what assertion this reason is correct or not.
Thank you.
Yeah. All right. So you were correct. CA is true and R is false. So let's move on to question number two. Which of the following um, statements is true based on the following figures? So you've been given about three figures, right? Three graphs. and it's a plot of X biomass and P product with respect to time. So you have A, B, and C. Okay, so you're seeing how the substrate is changing in terms of the product, right? Over a period of time. So the options that have been given to you are A. Figure A represents only non-growth associated metabolite production. Okay. Uh, Figure B represents the option B is figure B represents a mixed growth association metabolite production. Um, C represents a non-growth associated metabolite production, and D represents only growth associated metabolite production. So for you to solve this, you have to know what non-growth associated or growth associated metabolite production is. Do you have idea what that is?
No.
Yeah, that's not a problem. So what they're saying is in a non-growth associated metabolite production, the production of the metabolite is not, directly related to the growth of the cells. Okay. So it doesn't mean that as the growth increases, there will be an increase in metabolite production. Okay. And non-growth associated metabolite production obviously means the opposite. So growth associated metabolite production means that with respect to an increase in growth, you will see, directly proportional sort of growth of the metabolite also. And in non-growth associated metabolite production, you will see that the metabolite being produced is not exactly related, proportionally to the growth. Can you think of, examples of why or where this might happen? Why would a metabolite be associated with the growth, or why will it be produced not associated with the growth? Do you think you have come across any of these things? Not not clear about it?
Not sure.
Yeah. So, growth, non-growth associated metabolites could be metabolites which are produced in the cells only after a certain amount of time, right? Certain secondary metabolites are produced like that. So a cell has to be, growing for a certain amount of time for it to start producing it. Okay, so it won't be that as soon as the growth starts, the metabolite production also will start. It will be more like in the case of C, where growth has happened and only after some point will the metabolite production have started. So C, as you can see, is a graph that is showing a non-growth associated metabolite production. And graph A is a growth associated metabolite production. So you can see as the growth is increasing of the biomass, the product is also increasing of the metabolite, right? So now that I've explained this to you, what do you think the answer is? Which of them are true?
B and C.
B and C? Let's see if you're right. So yes, B and C are correct. So figure B represents a mixed growth associated metabolite production, which means that both of them are there. It's growth associated, non-growth associated, and C represents a non-growth associated metabolite production, right? Okay.
Okay.
Yeah. So we'll move on to the next question. So question number three is this. It's a statement, and you have to tell me whether it's true or false. So dioxide growth represents a phenomena in which substrates are used in sequential manner by cultures undergoing multiple lag phases. Is it true or false?
It's true.
It's true, right? So dioxide growth by the die you can tell. It's a prefix, right, which usually represents two. So dioxide growth represents a phenomena in which substrates are used sequentially. So if you have a culture in which you have given both lactose and glucose, the cells will not use both of them together. Like certain cells like E. coli are capable of taking using glucose and lactate as a carbon source, right? But like you might expect, if you didn't know about this dioxide growth pattern, they are not used both together. So that is why if you ever studied lac opron, you will know what this is. Have you gone through have you studied lac opron anytime?
Let me be very frank with you. I'm an engineer by profession,
Okay.
electronics engineer.
Oh, electronic engineer.
So,
Okay.
yeah,
So sometimes I tend to assume that you might be a biotechnology, BTech or MTech in biotechnology. So
I work for a
yeah,
I work for a firm
yeah.
which is producing vaccines.
Okay.
Thank
So
you.
yeah. So in this, what happens is the cells all eukaryotic, prokaryotic. Prokaryotic means bacteria uh, and archaea, right? And eukaryotic means the mammalian cells, plant cells. All of them tend to use glucose as their primary source. Like all of us can grow with just plain glucose, but we have also evolved to use different kinds of carbohydrates. Okay, so like in the case of E. coli, it's been known to be able to use a lot of different carbohydrates to get energy. Okay, so, if you give a media to E. coli in which it has both glucose and lactose, what happens is it will start using the glucose first. Okay, that because it's easier for it to use, because all of the organisms have a base in which glucose is our primary source of carbon. Okay, so it will start using glucose, and only when glucose gets over will it start producing the enzymes necessary to break down lactose. So that is where you are getting the two curves. So the first lag phase, lag phase will be when the cells are getting used to the media environment. You will see a slight lag, and then you will see a log phase where it's increasing, and that will be when these cells have started using glucose as their carbon source. Then you will see a lag phase again for these cells to start producing the enzymes which will break down the lactose, and then you will see a log phase, that is an increase again. Once they produce these enzymes, they will start taking up lactose as a carbon source. So they don't take it together. So that is what dioxic means in this case.
Are there more than two stages?
What?
When you say dioxic,
Yeah.
can they be more than two
Yes, yes,
stages?
yes. There can be
Yes.
more than two stages depending on how many different types of carbon sources you are giving them.
Okay. Thank you.
And each of these will be depending on whatever sequence they're taking it in. They will each have a lag phase and a log phase. Okay. So let's move on to question number 4. So a genetically engineered strain of bacteria is used to convert a substrate to product in a batch fermenter. In the exponential phase, which is the log phase, the specific growth rate of the bacterial system is given as 0.45 per hour. Okay, so which of the following statements is true for the system? And the options that you've been given is a doubling time and a division rate. Okay, so the only information that you've been given in this is that it's a batch fermenter and that the specific growth rate is 0.45. So with just the specific growth rate, we can calculate both the doubling time and the division rate, right? So let's do that. So the doubling time TD will be equal to ln 2 of the specific growth rate. So in this case, the specific growth rate is 0.45, right? So what you get, the doubling time is 1.54 hours. That means in this system, after every 1.54 hours, the cells would have doubled. Whatever cells you had initially, they would have doubled. Okay. And now that you know that the doubling time is 1.54 hours, you know that the inverse of that doubling time is the division rate. Okay. And so what you get is 0.65 per hour is the division rate of these cells in the batch reactor. So let's see if we have that option. So the doubling time being 1.54 hours, yes, and a division rate of zero point 0.6 per hour, right? It's an easy enough question, right? If you have the specific growth rate, you can find out both the doubling time and the division rate.
Uh, I think the doubling time is per hour
Yeah,
here.
it's yeah per hour.
Uh, could I just see your answers, please?
This one?
Yeah, no, the next slide.
Okay. This one?
Yeah,
Okay. So I think the R minus one has gone
yeah.
first.
I'm sorry, sorry.
No, no, no problem. So wait, I think doubling
I
time
think
is R only, not R minus one. Only
yeah.
division
So
rate is R minus one. So I think the
the
answer is
answer would
B.
only C, I think.
Yeah. No, no. So in this case, it's better if you choose both A and C, because I think this is a mistake on the part of the people who have written it, right?
Okay.
Okay.
Right.
So doubling time, let me just check the unit of doubling time. Yeah, I think it is hours. Yeah, it is hours.
So
Okay.
the answer would be only C, I think.
Yeah, but since you can, argue if you see that you've been marked wrong in this and you've chosen both the doubling time and the division rate, right? Since they're asking you, this is a sort of not a trick question, it's sort of a mistake on our part, right? So you might
Okay.
encounter questions like this. So you can choose both A and C or C, and depending on what the answers they have selected for the final result, right? You can
Okay.
argue. They will give you a
Thank
chance to argue, right? A crib
you.
session
Okay.
sort of thing.
Thank you.
So you can do that. Okay. So question number 5 is uh, Ximomenus mobilis is used for the conversion of glucose to ethanol in a batch fermenter under anaerobic conditions. In this case, that means you have no oxygen in the system or very minimal oxygen in the system. For this system, assume the following conditions. The endogenous metabolism cannot be neglected. Okay, do you know what an endogenous metabolism is?
The At the end, I think it's the organism consuming a part of its own reserves.
Yeah. So what happens is after it reaches the stationary phase, right? After the log phase is over and the amount of nutrients have very drastically decreased, the cells tend to die, right? Okay. And when these cells are dying because of the lack of nutrition, they get lysed and they release their, inner contents into the media. Now the inner contents will be things like proteins and carbohydrates also, right? So these can be used by other cells in the culture itself to keep growing. So you will still see a slight growth, okay? Even though there is almost no nutrients left in the media that you had originally given, because there are cells which are dying and those are being used up by cells to, enhance their growth. Okay,
Thank you.
so that means the endogenous metabolism is there. Okay, consider the cells to be in exponential phase where the specific growth rate can be approximated to the maximum specific growth rate. Okay, so which of the following biomass accumulation rate equation is correct for the given batch system? Okay, so let's start doing this first. So when you see mass balance, so what you know is whatever accumulation of biomass you're having will be equal to whatever input you're given minus the output plus whatever is being generated minus the consumption, right? This is something that we had discussed in the last session. So in a batch system, you can see that the input and output is zero. So you're not putting anything in the system or removing anything from the system at different times, right? You have put the initial amount of media and inoculum, and you will wait for the system to completely, for the process to completely get over before removing it. So you don't have an ongoing input and output mechanism. So that is zero. Okay. So the input and output will be zero. So all that is left is the generation minus consumption. and that will be equal to the accumulation. So the accumulation term will be the dxv by dt. So the change of the biomass and volume in the volume by over a period of time, right? And that will be equal to the generation, which will be equal to the specific growth rate in biomass into the volume, and minus the consumption rate, right? Where Kd will be equal to the endogenous metabolism and the death that is happening of the cells into the again the biomass and the volume. So these three units are representing that. This is representing the accumulation, this is representing the generation, and this is representing the consumption. Okay. So now, since all these have the V, unit of V, and we since it's a batch system, the volume does not change at all, right? You're not adding or removing any media, so we can see that the V is constant. So we can cut V from all of this. So if you divide this entire equation by V, you can cut V from all of this. So what you're left with is dx by dt and u minus kd into x. Since you can take u and kd, mu and kd outside, since they both are being multiplied by x, right? So you get this term. Okay. So after this, what you have to do is integrate on both sides from t equals to 0 to t equals to 10, assuming that the reaction has taken from 0 to a time t. Okay. And the biomass will be from 0 to x equals x naught to biomass at whatever time t is there, right? So as per the question, we know that the specific growth rate is equal to the maximum specific growth rate, right? So what you get is ln x by x naught equals to mu max minus kd into t. Okay. And the closest option that is given to you in the questions will be ln x naught by x equals to kd minus mu max into t. So the answer is A. Were you able to understand this? Why we have done what we have done? Or should I explain it just once again?
I think the option B uh,
Is
is
correct.
ln x ln because that's the mu maximum is kd by t into t.
Ln x naught by x. Huh. So option B may the problem is mu max by minus. What is the problem?
Oh, I'm okay. Okay, sorry.
No, no problem. So the thing is, since option A and B both have x naught by x, right?
Okay,
So
fine.
you have to reverse this also. So KD comes first and mu max comes second. That is what has happened here.
Okay, fine.
Okay, since all of them is ln x naught by x instead of ln x by x naught, right? So that is why we have to, change this. So
True.
instead of
True.
mu max minus kd, it will become kd minus mu max. So that
Thank
is
you.
why option B is not correct. Okay, so the closest answer that you're getting is A in this case. Okay, so were you able to understand how and why we solved it like that, the last question?
Yeah. Yes, I got it.
Okay.
Thank you.
So let's move on to question number 6. So you have to identify the mass balance equation for the microbial cells in a bioreactor under batch operation. Okay. R1 is the rate of input of cells, R naught is the rate of output of cells, Rg is the rate of generation of cells, and Rd is the rate of consumption or death of cells, and dA by dt is the rate of accumulation of cells. It is similar to the question, it's just that instead of the terms, I have given you symbols. So in a batch reactor, we've just done this. In a batch reactor, input and output are zero, right? So you can get rid of both Ri and R naught. Okay. And the only thing you will be left with is Rg, Rd and dA by dt. So since dA by dt is accumulation and generation minus consumption is what the accumulation is, right? So the correct option will be C. It's just a sort of trick question so that you keep in mind the symbols that are being used instead of just the word. Okay, this is a simple enough question. You got that, right? This one is a simple question.
Sorry, yes.
Yeah. Okay. So the option is C. So let's move on to question number 7. In a certain bioprocess involving a high value product, the microbial cells have a low conversion rate of substrate to product. Okay. The accumulation of product also causes a reduction in this conversion rate. Which of the following operation modes is the best for this bioprocess to achieve efficient conversion? So you know that do you know the difference between batch, fed batch, and continuous?
Yes, yes,
Yes.
ma'am.
Okay. So what they're saying is you have a very high value product. Okay. So what you want is the maximum amount of this product that you can get. And the microbial cells have a low conversion rate of substrate to product. Okay, so you take, for example, certain secondary metabolites. Okay, the cells don't frequently produce them. They're not produced in large quantities because they're not of very main importance for the survival of cells. So they're produced in a very low rate. A lot of chemotherapic drugs are produced by plant cells, right? Like Vingarosia, periwinkle plant, produces a drug called vincristin and vinblastin. Okay, but they are produced in very small amounts because they're secondary metabolites. So a primary metabolite will be something that is required for the cells every day, every time purpose. So enzymes or products that are used in maybe glycolysis or any of the normal cell division, etc., will be primary metabolites, and certain metabolites which are maybe used only when the cells are undergoing stress, heat stress, cold stress, or antibiotic stress. Only that time this secondary metabolite will be formed. And so even when you're giving this stress, right, they are formed in very low amounts compared to the primary metabolite. But in this case, since it's a very high value product, you want the most you can get out of it. So the accumulation of this product also causes a reduction in the conversion rate. So what happens is cells have a feedback loop, right? So when they sense that their surrounding, or if it's produced inside the cell, that a certain maximum concentration of these secondary metabolites is reached, there's a negative feedback loop. Okay, so what that does is, as the concentration of that secondary metabolite has reached a level, it will, sense the system will sense it, and it will make sure that the secondary metabolite is not being produced anymore because it's reached the maximum, amount that is required by the cell. Okay, and if it's produced outside the cell and it's in the media, the same thing can happen. It will still be sensing the amount of the secondary metabolite in its environment, and once it thinks that a certain concentration has been reached, it will stop producing the secondary metabolite. So that is why the accumulation of this product reduces the conversion rate. Okay, so with respect to these two informations that has been given to you, which of the following modes of operation do you think is best? Is it a continuous operation, batch operation, fed batch operation with product removal, or both continuous and fed batch operation with product removal?
In D, ma'am?
D. So yes, the answer
Yes.
is D. So it can be both continuous. So what happens in continuous is, since the media and cells are being continuously removed, right? So you're not reaching that high point of concentration in which the cells start reducing the conversion of the substrate to the product. And again, in fed batch also, you can keep removing the media and adding new media, so that again that maximum concentration is not removed. The only one that you can't do is a batch operation, since you're not removing media at all. At one point the concentration of the secondary metabolite will reach that point, and the conversion of the substrate to the product will stop. Okay, so If you are clear with this question, I'll move on to the next question.
Yes, yes, ma'am. Thank you.
So the question number 8 is, what is the lag phase? So we talked about dioxic growth, right? So growth of cells have a pattern. Growth of cells in an external in vitro environment where you have given them media, it has a pattern. Okay. So what is the lag phase in that? So in a growth rate, what you can see is a log phase, a lag phase, stationary phase, a decline phase, right? So what is a lag phase in that? The options are a period which results from nutrient depletion or toxin accumulation,
See, ma'am.
a period in which there is no change in cell concentration, typically at the beginning of a batch growth. And yes, that
Yeah.
is correct. The lag phase, as the name sort of indicates, is the lag you see before cells start growing. So even if you are doing the passage, right, in which you're or the change in which you're taking inoculum from one culture and moving into fresh media, you will still see a lag phase. Okay, it will be less, but you will still see a lag phase. The lag phase will be very high if you are moving these cells from one media to a different kind of media. So if you are moving E. coli cells from a nutrient media to a sort of synthetic media, okay, since the media is different, you will see that a lag phase is bigger because the cells have to get accustomed to the new media, right? New temperatures, or in case you've taken it directly from a freezer stock which has been stored at -80 and it's going into these cultures, that temperature change, and for the cell to revive, that will be the lag phase. Then you will have the exponential phase or the log phase, a stationary phase, and this is stationary because the amount of cells that are dividing and the amount of cells which are dying are the same. So the growth of the cells and the death of the cells is the same. And at one point, you will have a death or decline phase where the death rate has taken over the growth rate. Okay. So the answer is
I'm sorry. Please go ahead.
yeah, yeah. The
Yeah.
answer is C. What is your doubt? Now you can tell.
In the vaccine industry,
Yeah,
when you just talked about passage,
yeah,
you got a master cell bank, you create your working seeds,
yeah,
and you allowed say 4 or 5 passages.
yeah.
Now, in a then continuous continuous fermentation,
Yeah.
would the level of passages change?
In this case, technically we're not passaging, right? Since we're just giving fresh media. In this case, what I think of when I think of passage is the fact that we're moving the cells to a completely fresh media. In this case, it's not passage, but the amount of doublings that these cells can undergo will be the same, since
Okay.
right, that mammalian cells have um, a certain number of times only that they can divide before they stop growing altogether. This problem is not there with bacterial or fungal or plant cells, but animal cells have this problem. All
Uh,
yeah.
no, basically, I'm talking about the bacterial cells
Bacterial cells may. So what you're saying, asking me is uh, the
in a
passage.
continuous culture.
In
Yeah.
a continuous culture, passage will be the same.
Okay. Yeah,
No,
I'm asking.
I
I'm
think I
asking.
didn't understand the question. So can you repeat it? I'll try this time.
See, basically,
Hmm.
when we in the people in the vaccine industry,
Yeah,
after you take the master cell bank,
yeah,
you go to the
yeah,
working cell bank. Basically, you want to have your master
yeah.
in the and you're allowed say 3 or 4 passages
Okay,
of your cell bank
okay.
for using as a uh,
Inoculum.
inoculum.
Okay.
Yeah. Now, in a continuous culture, when I do a continuous fermentation,
Hmm.
let's say I've introduced inoculum,
Yes,
and that being continuous
yes,
because it's going continuous.
yes.
So basically,
It's not being passaged at all.
okay,
So it is not like it is a big, passages when you have sort of reached the maximum confluency and you're uh, shifting the cells to a newer medium so that they can continue to grow, right? But in this
Okay.
case, since you're giving a uniform condition throughout the time, you have given the same temperature, there will be no lag phase at all. So these cells are continuously in exponential phase after the initial lag phase that they had faced. So it's not technically passaging, it's just
Okay.
growing in a very continuous, indefinite form.
Okay. Thank you.
Yeah, no problem. So this is question number 8. The answer is that a lag phase is a period in which there is no change in the cell concentration, and it is typically at the beginning of the batch growth. Okay. So since lag phase and stationary phase both are parallel to the x-axis, do you think they're the same? We know that different
Mm,
conditions lead to this, but do you think live cell wise it's the same or not? The amount of live cells that will be present in lag phase per ml and the stationary phase, will it
no.
be? Yeah, because most of the cells that you put in the lag phase will be alive, just not dividing. But here you will have an equal amount of dead cells and live cells. Okay. So let's move on to question number 9. An industrially important enzyme is produced from a thermophilic bacteria. Okay. So do you know what a thermophilic bacteria is? Thermophilic, mesophilic,
Which requires a high temperature.
which can
And they get a
prefers
high.
to grow in a high temperature. Yes. So a thermophilic bacteria in a bioreactor operating in batch mode. So 50 liters of media was inoculated using 8 grams of cells. Okay. So the amount of cells that you have is 8 by 50, right? That is the amount of cells per liter that you have in that batch mode. Oh, wait, there are people trying to join. Okay. Yes. So, um, as I was saying, for the person who has come now, I will finish these questions, and then if you want, I'll go back and start again. Okay. Is that okay with you, Rosalind? You can just write yes or no in the chat. No response. So she left. Okay. Oh no, she said. So as I was saying, I will. This is the ninth question. There is 9 and 10, and after I'm finished explaining that, I will go back from the first question and explain once more. Okay. Since you've joined now. Okay. So as I was saying, an industrially important enzyme is produced from thermophilic bacteria in a bioreactor operating in batch mode, and 50 liters of the media was inoculated using 8 grams of the cells. So the lag phase was found to be 60 minutes. Okay. The maximum specific growth rate of the organism is 0.36 per hour. Okay. Under these conditions, calculate the cell concentration after 6 hours of growth. So you know that there is a lag phase of 60 minutes. Okay, you know that the specific growth rate is 0.36 per hour. So you have to calculate. You know that in 50 liters of media, that is there is 8 grams of cell in total. So you have to calculate the concentration of cells in this 50 liters after 6 hours of growth. Okay. So this is the data that has been given to you. How about you just try to figure out how much, with whatever you have understood, just try to figure out how you might go about it, and tell me if you have come to an answer. Give me just any approximate answer of the amount of cells that you think will be there. So just try thinking in terms of how this is happening. So you have 50 liters, right? You have put 8 grams in it. Okay. So like you can see here, the amount of biomass x naught at the starting is 8 by 50. So 0.16 gram of cells is there per liter. Okay. And the specific growth rate is 0.36 per hour. Okay. And you know that there is a lag phase. There is a straightforward formula to answer this, but I just want you to understand what is happening. Okay, so you know that there is a log phase about 60 minutes and the lag phase will only start after that 60 minutes, right? So 6 hours minus 60 minutes, 60 minutes, right? Yeah. So that means 5 hours. The growth is happening only for 5 hours, right? Because the lag phase mein there is no growth itself happening. It's a lag phase. Okay. So I will give you the formula, okay, and the answer to. Just see if you know what is going on in this case. Okay. So this formula is to, if you have the lag phase, the specific growth rate, the initial concentration and the final concentration, it will give you the time that it takes to reach that final concentration. And so you manipulate it so that you can figure out what the final concentration is in this case. This in this you're getting the time that it takes to reach that final concentration, but since we know the time, what we need to find is the x, right? So you can note down this formula. It's not something that I think has been taught in the course, but it's something that you might require, right? So it is 1 by nu, which is the specific growth rate, ln of x by x naught, where x is the final concentration, x naught is the initial concentration, plus t equals to 0. That is the amount of time that has gone in the lag phase. Okay. So if someone asks you how much time did it take for the cells after you inoculated for it to reach this concentration, you will tell the total amount of time, right? You will not minus the log phase, the lag phase from it. Okay. So this is keeping that in mind. So if you want, you can try and do the calculation to see if you're getting this answer or not. So if you put in all these values, 1 by the specific growth rate, which is 0.36, ln of x, since you don't know, by 0.16, which is the initial biomass concentration, plus 60 by 60. In this case, why are we doing 60 by 60?
Minutes to hours.
Yeah, since the growth rate is in hours, right? And the amount of time that has been given to you, t, is also in hours, you will convert it into hours. So what you get is time equals to 0.96 grams per liter. Sorry, x equals to 0.96 grams per liter. I'll change this. Just one sec. X equals to 0. So what you are trying to figure out is x, right? So what you see is x, that is the concentration of biomass at time equals to t, which is 6 hours from the time that you've inoculated it, is 0.967 grams per liter. Okay. Do you have a doubt in this question?
No, sorry.
No?
No,
Okay.
no.
Rosalind, did you understand? You can write it in the chat if you're not comfortable talking. I don't know if I'm audible to her. Okay, yes, sure. Thank you. Okay, so let's move on to the next question. So, question number 10 is glucose is being used for the production of E. coli in a 1200 meter cube bioreactor, and 60 grams per liter of glucose is being fed into the system with a substrate conversion of 95% in the process. Okay. So what that means, let's just figure out what this till the sentence means. So you have a bioreactor and you know the volume of the bioreactor. Okay. Total volume of the bioreactor, which is 1200 meter cube. Okay. And you have 60 gram per liter of glucose. Okay. That is put in the system. and a conversion rate of 95 in the process. So 95% of the glucose is being converted into biomass and only 5% will remain. Okay. The biomass yield from the substrate is 0.55 gram per gram. Okay. Assume that the specific growth rate is approximately equal to the maximum specific growth rate, which is zero point 0.5 per hour. For this batch mode of operation, the initial cell concentration is zero point 0.1 gram per liter. So when you started, you put it so that there is zero point 0.1 gram per liter of cell. And the downtime between batches, that is, once this batch has given the maximum amount of cells and you have removed it, you add fresh media and fresh inoculum. The time between these two events happening is 20 hours. Okay, since a system should not be kept running continuously, right? So you give a downtime. In this case, it's 20 hours. So you have to calculate the following things. Okay, so first is calculating the batch time. Okay, so how much time does it take? Okay, in terms of hours for it to reach the final concentration, maximum concentration that you can get. So this has a formula that you would have been taught. TB is the batch time, 1 by mu max, which is the specific maximum specific growth rate, ln 1 plus y x by s. Okay, in y x by s is the biomass yield from the substrate. Okay, by x naught, which is the initial biomass, multiplied by SO, which is the amount of substrate that is there initially, minus SS, the final substrate. Okay, so SO, it is 60 gram per liter, like they had said here, 60 gram per liter of glucose is being fed into the system, right? And the conversion rate is 95. So only 5% substrate remains at the end of this batch. Okay. So if you see that you've converted the 5% to a normal number by dividing it by 100, right? And you multiply it with 60, which was the initial amount that you have. So you have 6 gram per liter of glucose left at the end of this batch system. Okay, and X naught is zero point 0.1 gram per liter. That is the inoculum that you had added initially. Okay, and the conversion rate or of the substrate to biomass is 0.55. The mu max is zero point 0.5 per hour. So if you input these things here, okay, you get 11.5 hours. So one batch reaction takes 11.5 hours to complete. Do you guys have a doubt in this? Something that you didn't understand? Since it's a straightforward, plugging in values into equation, you just need to know the equation. Do you guys have a doubt? I'll move on to the next question otherwise. Okay. So no doubt. Okay, sure. So now you have to find the total mass of cells produced per batch. So since one batch is 11.5 hours, you have to figure out total mass of cells produced. The initial mass of cells produced was zero point 0.1 gram per liter, right? You need to know the total mass that is produced. Okay. So in this case, XF, the biomass that will be there finally, is equal to X naught, which is the initial biomass, into E, the Euler's number, which is uh, E to the power of the maximum specific growth rate into the batch time. Okay. So since you've just calculated the batch time, which is 11.5 hours, and the maximum growth rate is 0.55, right? uh, uh, Sorry, zero point 0.5, a Euler's number, and zero point 0.1. So if you plug in these values and calculate it, you will get the final biomass uh, in that batch to be 31.42 grams per liter. Okay, but now you have to find the total mass of cells produced per batch. So it is not in terms of per liter. Whatever the total volume of the bioreactor was, you want to figure out how much exactly is there. Okay, so now that you found the per liter value of the biomass, you can multiply it by the volume of the bioreactor, right? So, since xf is given in a unit of L. Like I told you last time also, you have to make sure that there's a continuum in units, right? So, and the volume of the bioreactor has been given to you in meter cube. You will have to multiply it by 1,000 to get, you know, the amount, the conversion, to get the conversion of the volume from meter cube to um, the liter. Okay, so the total mass of cell produced. Okay, so the total mass of cells produced, you will have to subtract the initial mass that was there, since that is not being produced. That is the mass that was already present, and that is the mass that you've already given to the bioreactor, right? So that is xf, that is the final biomass, minus the x naught, which is the initial biomass, into the volume of the bioreactor. So you know the xf that we found now is 31.42, and you subtract zero point 0.1, which was the x naught, okay, and you multiply it by the volume in meter cube that is given to you of the bioreactor, and 1,000 for the conversion into liter. So what you get is 37,583 kg, okay, of total mass is being produced in that bioreactor after 11.5 hours. So, if you have doubts, just speak up. Okay, I'll move on to the next question. So now, what you have to calculate is the total number of batches that you can have in a year. So now you know that a single batch is for 11.5 hours. Do you have a doubt, Ganesh? So you know that one batch of in this bioreactor takes 11.5 hours, right? Because that is what you found out in the batch time. Okay, and you also know that in the question itself it was given that the downtime between batches is 20 hours. Okay, so you have to take that also into account. So the total time for, if you think of the downtime itself, also including the time taken for one batch, okay, it will be 11.5 hours plus 20 hours. So for that one batch, you have to take this much amount of time, the 11.5 hours for the growth to happen, and 20 hours of downtime. So totally you need 31.5 hours for one batch to take place, and for before you start the next batch. Okay, so it is 31.5 hours. Okay, and the number of batches carried out in 1 year. Okay, that is 365 days into, if converting it into hours, you will take it multiply it by 24, so you will get the amount of hours that are there in 365, right? And you will divide it by the number that you've gotten here, 31.5. Okay, the answer is 278 runs. So that means in a year, uh, with batch time of 11.5 and a downtime of 20 hours, you can have 278 runs of this bioreactor. Okay, do you guys have a doubt in regards to this? No? Sure. So the fourth in this is the total mass of cells produced annually during the batch culture. So now you know how much total mass of cell is produced within one batch, which is 11.5 hours, and you know the number of runs that can happen also, right, in a year. So all you have to do is multiply that amount, the total biomass produced in one run, into the total number of times in a year that the run can be performed, and you get 10 10,448 tons per year. Okay, this is us. Oh yeah, one more thing I forgot to mention is, in each of these questions, you guys are able to see that they are asked in a specific uh, unit, right? So make sure that when you're calculating it, you make sure the units are right. Okay, so when we calculated the total mass of cells produced in a batch, it was in kgs, right? So when you have to convert kg to ton, do you know how to do that? What will you have to do?
Uh, kgs to ton is divided by 1,000.
Divide by 1,000. Anyone else? Yes, almost divide by 1,000. It is technically, 907.185. Okay. So 1 US ton is 907.185 kilogram. Okay.
Okay.
So since it's nearby to the, you know, since US tends to not use the SI unit that is followed around the world, right? It is not exactly like in our case, kilogram, gram, decagram, all that thing is a single unit, right? So in this case, ton is not exactly 1,000. So it is
But
907.
metric ton means,
Hmm?
okay, fine.
Hmm.
It's a metric ton which I was talking about.
Yeah. Okay. So since it's nearby to 1,000, you can do that. You divide it by 1,000 and you get the amount. Since the one in kg would have been very high, right? So what they've asked for is ton. Okay. So the last question for today is if the desired annual biomass production is to be instead of 10,448 tons, right? It is to be 15,000 ton a year. What should be the volume of the bioreactor? Okay, so you're not changing the amount. You know that the amount of cells that you can get from a certain volume does not change in this batch reaction, right? So the only thing you can change to get a higher amount of biomass is to change the volume of the bioreactor itself. And then how will you do that? Okay. So the annual biomass production is the total amount of biomass produced into the number of batches, right? So what you need, so in this case, you know what the annual biomass production is. So you know it's 15,000 tons per year, okay? And you don't know X. What is the amount um, that is required in one, since you don't know the volume itself, you don't know the amount of biomass that is to be produced per, yeah, you don't know the amount of biomass that is to be produced per run, right? Since you don't know the volume, that is what we have to calculate. But you do know the amount of batches. Since you're not changing the downtime, right? And you're not changing the batch time also. You know the batch time and the downtime. So you know how many uh, batches can be run in a year. So once you plug in the values, and since x is the unknown, you will get x required equals to 53.96 tons. Okay. So now that you've gotten that, okay, so you have to calculate the total mass of cells produced during the batch culture. Okay. So X required is equal to X final minus X naught into the volume required, right? So X required, you know, okay. So that is the amount of cells produced, total biomass produced per run is 53.96 tons. And you know the XF, the final amount that is produced, and the initial amount that you had put also, right? You had figured out here the final amount 31.42, right? So you know the initial amount 0.1 grams per liter that you had put and the final amount 31.419, and what you have to find is the volume required now, right? Okay. So once you calculate this, you will get the volume required directly, and it is 1722.8 meters cube. Was that, did you guys understand how it is done? So in this case, you're sort of back calculating to the beginning instead of the end. So what we had done in the previous questions was we had been given these data and we were going around finding things in this manner, right? But now the final result has been given to you and you have to go around finding the initial thing. Okay. Do you have any doubts in these questions? No? Okay. So that is the final question for today. For those who join late, I will start from the beginning again. But since Aroil has been here since the beginning, nothing new is going to happen. You can leave the meeting if you want. For the others, if you would like it, I can, start from the beginning. Is that okay with you, Ganesh and Rosalind? Should I start from the beginning? Ganesh has left the meeting. All right, Aroil, let's meet next time. Thank you.
Thank you, ma'am. Thank you very much. Thank you.
So, Rosalind, are you there in the meet? Should I start from the beginning? You were only there for the last two questions, right? Rosalind, are you there in the meeting? Can you just respond in the chat? I'll start from the beginning if you're there. Or if not starting from the beginning, do you have any doubts? Since these videos will be put online anyway, do you have any doubts regarding the questions that we have done? Did you understand how to solve these? Roslyn, are you able to hear me? You can just write in the chat.
Yes, ma'am.
Yeah, okay.
Yes, ma'am.
So, should I go from the start again, just once for you?
No, ma'am. This
But
is
uh,
actually I joined in the late.
no, that's okay. We still have
I'll
time
go.
till 8 o'clock. That's why I asked you. I
No, ma'am. I'll go to the.
did you attend the Friday session?
No, ma'am.
Okay. So
Actually, I was not aware about this. True. Today only I got this
okay.
actually link.
Yeah, okay. So there are two sessions. One is on Friday and one is on Monday. Okay, same time it is 6 to 8. We'll be having this
Okay.
problem solving questions. Well, we'll give you, sample questions that are somewhat related to the assignments that you will be having. And once your assignment due dates are over, we can discuss that also in case you want. And you start,
Actually,
yeah,
in the assignment,
yeah,
in question assignment 3, I need to submit. I solved there is a doubt in question number 5.
yeah.
That
So
answer is not matching actually.
So the thing is, right now we've been told not to discuss any of the assignment
Yeah.
questions
No, no.
till the due.
Actually, I have solved it correctly. I know I have confident that
Yeah.
there may be some option wrong is there. Actually,
Okay.
it is coming around 43 point something. That is not there in the
So
option.
if that happens, what we usually do is once the due date is over, right? They will release the correct answers, right?
Okay.
So at that point, there's a discussion forum, right, in the NPTEL MOOC, page. There's a discussion forum, right? So there, if you
Okay.
write that, in the discussion forum, if you write, oh, I think this is the answer, but the option wasn't there, they'll give you marks for it. They will change it then, and you will
Okay.
get marks for it. Okay.
And ma'am, now we can do it or after the release of the score?
Now you can do it. If now also you can do it. If they think you are correct, they will change it now itself.
Okay.
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 I say this because I think last time when I was taking course, people realized that this might not be the correct answer after the results were released for the answers were released for the course. But you can do it now also. That you're getting this,
Okay.
and you know it's the correct answer, but none of the options are correct.
Mm. Yes, ma'am. I solved in each step I was getting the answer, but in
Yeah,
the last
last.
step only
Yeah,
it should be multiplied with something, but that answer is not coming.
yeah. Okay.
Mm.
So in case yeah, uh, the answer is wrong, they will change it. Okay, so you can do that. So on Fridays and Mondays, on Mondays I will be taking, and on Friday, one of my colleagues from IIT Madras will be taking it. And
Okay.
it's a problem solving question. The questions will be somewhat similar to what you're getting in assignment. So
Okay.
so going through these, it will help you to solve the assignment questions. Okay,
Okay.
and uh, the questions will be the same, so almost same. So there will be only a 2 3 question difference between what she is taking and what I am taking. Okay, so you can
Okay.
choose to go to whichever is comfortable for you time wise. If you're free on Friday 6 to 8, or if you're free on Monday 6 to 8, you can join.
Okay.
Okay,
Thank
and
you.
we'll be putting these videos online also, and the link will be there, so you can watch the videos also whenever you're free. And if you prefer it, right now also I can repeat it since I have time.
No, ma'am. No, ma'am.
Sure. All right. Since
Can you leave, ma'am?
yeah, you can use. Sure.
Thank you.
Bye bye.
Bye bye.